Welcome to This Explainer. Today, we are going to dive into how one man's absolute obsession with measuring light accidentally triggered a massive crisis, one that completely overturned classical physics. Imagine trying to measure something so incredibly fast and so elusive that just the mere act of trying to pin it down shatters our fundamental understanding of space and time. Well, that is the lasting legacy of Albert A. Michelson.
So how exactly did a failed experiment change physics forever? To understand that, we have to look at a shocking scientific failure that ultimately paved the way for Albert Einstein's theory of special relativity. It's this wild story of incredible precision, deep curiosity, and basically breaking our understanding of the universe completely by accident.
Okay, Section 1. The ether wind crisis.
To really understand this crisis, we need to set the stage with the single biggest scientific assumption of the 19th century. Back then, physicists widely accepted that light needed a physical material to travel through. Think about it for a second. Sound needs air or water to ripple through, right? Otherwise, you just have total silence in a vacuum. Ocean waves need water, so they naturally assumed light worked the exact same way. They called this invisible theoretical medium the luminiferous ether, and they believed with absolute certainty that it simply filled the entire vacuum of space.
Now, because the Earth orbits the Sun, literally hurtling through space at tens of thousands of miles an hour, scientists believed we should be able to feel an ether wind as we push through this medium. It's exactly like sticking your hand out of a moving car window. Even if the air outside is totally still, the car's forward motion creates a relative wind against your hand. Physicists were just absolutely convinced this ether wind was out there, just waiting for someone to build an instrument sensitive enough to detect it.
Section 2. A Naval Academy prodigy.
To understand who finally put this invisible wind to the test, we really need to look at the meticulous man behind the lens. Albert A. Michelson was a Polish-Jewish immigrant, born in Prussia in 1852, who moved to the United States when he was only 2 years old. He actually grew up in the rugged, dusty mining towns of California and Nevada right during the gold rush era, which makes his eventual destiny all the more fascinating, honestly. His path to science wasn't this traditional journey of elite academic grooming. No, President Ulysses S. Grant actually awarded him a special appointment to the U.S. Naval Academy in 1869. So leaving those rough mining camps behind, he excelled in the super-disciplined world of the Navy, specifically mastering optics and technical drawing, eventually graduating as a midshipman.
When someone asked him later in life why he spent so much time studying light, Michelson gave this beautifully simple answer. He said, "Because it's so much fun." I think that tells us everything we need to know about the guy. He wasn't just some stoic naval officer dryly following orders. He was a really curious tinkerer, driven by the pure, unadulterated joy of scientific discovery. He just loved the mechanics of it, the challenge, and the sheer beauty of light itself.
Section 3. Chasing the speed of light.
That joy translated into a lifelong, meticulous obsession with measuring the exact speed of light, continuously refining his methods over decades. In 1879, while serving as a naval instructor, he set up this improvised equipment along the seawall of the Naval Academy in Annapolis. With immense care, he measured the speed of light in air and published an incredibly precise figure, 299,910 kilometers per second, give or take 50 kilometers. Keep in mind, this was 1879. Achieving that level of accuracy without modern computers, lasers, or digital timers was absolutely staggering. He was quite literally pushing the absolute boundaries of human measurement.
So how did he do it? Well, he refined earlier techniques using an ingenious mechanical marvel, a rotating mirror setup. He basically generated a light source, directed it through a tiny slit toward a rapidly rotating mirror, which then bounced the beam to a fixed flat mirror a set distance away, before reflecting it all the way back. By measuring the slight visual displacement of the returning light on a plate and knowing the exact rotation speed of his mirror, he could calculate the speed of the light beam. To pull this off accurately, he relied heavily on sheer statistical rigor, taking independent, repeated measurements to reduce any variability and weed out systematic errors.
And his obsession with precision continued late into his life. Let's fast forward to 1929 to see just how deep this obsession went. He collaborated on building this absolutely massive 1.6-kilometer-long, 3-foot diameter steel tube in Southern California. Just think about the sheer scale of that engineering effort. His goal was to pump out the air to create a near-perfect vacuum, bouncing light paths back and forth to equal 5 miles in total distance. He wanted to completely remove any atmospheric haze or smoke from his measurements to get the purest possible speed of light.
Section 4. the famous null result. It's wild to think that it was actually his work decades earlier, back in 1887 with his colleague Edward Morley, that inadvertently broke the laws of classical mechanics. Michelson and Morley set up this incredibly precise interferometer, which is a device that splits beams of light to measure minute differences in distance. They were aiming to finally measure that ether wind we talked about earlier. They fully expected a clear result. The ether wind should cause light to travel at slightly different speeds depending on which direction the light was pointed relative to Earth's motion through space. But when they actually looked at the data, a completely null result. Nothing. No wind. No ether. The light traveled at the exact same speed in every single direction, no matter how the Earth was moving. This null result created an absolute crisis in physics. The fundamental medium of space that scientists had relied on, the ether, simply did not exist. It completely backed the scientific community into a corner, making them rethink space, time, and motion from the ground up. Ultimately, this very failure laid the groundwork for Albert Einstein's theories of relativity. In fact, Einstein later noted in an interview that he wasn't even consciously influenced by the experiment directly. He just took the profound truth of Michelson's null result for granted when he was developing his own revolutionary theories of a universe without ether.
Section 5. A lasting scientific legacy.
Let's look at how Michelson's instruments didn't just break physics in the 19th century, but are still actively used to explore the cosmos today. For his unparalleled optical precision instruments and the groundbreaking investigations carried out with them, Michelson was highly awarded. He made absolute history. In 1907, he became the very first American to ever win a Nobel Prize in a science.
And his technology quickly evolved way beyond earthbound experiments. He actually invented astronomical interferometry. This is this fascinating process of combining light from two or more separate apertures to measure celestial objects with extreme high precision. It essentially lets astronomers resolve details on objects that would otherwise just be blurry, indistinct dots in a standard telescope.
In 1920, applying this exact principle, he and Francis G. Pease made astronomical history. They used a clever periscope arrangement with subpupils, which are essentially smaller secondary openings used to capture and combine separate beams of light, spaced 20 feet apart. They attached this whole rig to the massive 100-inch Hooker telescope at Mount Wilson Observatory. And with this setup, they successfully measured the diameter of the immense red giant star Betelgeuse. Think about how incredible that is for a second, using 1920s analog technology to measure the physical width of a star located billions of miles away. It was the very first measurement of the diameter of a star other than our own sun.
And his legacy doesn't even stop at stars. Today, physicists use massively scaled-up versions of Michelson's interferometers to detect gravitational waves, the literal stretching and squeezing of space-time itself, caused by cosmic events like colliding black holes. These modern facilities feature 4-kilometer-long vacuum arms set at 90-degree angles. Why so big? Because a passing gravitational wave slightly stretches one arm while shortening the other by just a fraction of a proton. Michelson's 19th-century foundational concept is sensitive enough to detect this microscopic change. By the year 2020 alone, this technology had successfully observed 15 distinct gravitational wave events, opening up an entirely new field of astronomy.
The absolutely crucial point to take away from this explainer is that an obsessive pursuit of precision can accidentally reshape our entire understanding of reality. As we consider Albert A. Michelson's incredible legacy, we really have to ask ourselves, what current scientific laws, what facts we accept as absolute certainties today might be completely broken by the next generation of curious tinkerers who are just trying to meticulously measure the universe? Thank you so much for joining me for this explainer, and keep questioning the certainties around you.